Alright, we're recording.
Good morning. I'm Jed.
My name is Andre.
Eli.
And Brandon.
Start us off with my 3.5 play. Here I have my questions posted. This is my actual work. So I did number 13. 4 cosine of x sine of y equals 1. So what I did is I took it's a product rule since these are multiplying by each other. So I took the derivative first one times the second one plus first one times by the second derivative, or sorry, this second one's derivative. One over there. Do that, you'd get negative 4 sine of x sine of y plus 4 cosine of x, and with this one, it's going to be cosine of y times by y prime. It's dy respect to dx. Then I showed it here that I was moving everything to the right side except for y prime. Y prime is equal to 4 sine of x sine of y over 4 cosine of x cosine of y, which is just tan xy.
All right.
Yeah, that looks good. I know I personally I didn't do that one yet. But I mean it looks good, like you did all the differentiation rules, and for especially for the implicit, you added the dy over dx for all the y's and stuff. That
Yeah.
looks good, yeah.
Yeah.
I agree with that.
Looks good.
All right. Let's see. All right. So I did for 3.5, I did number 49. Oops, I got all my work down here. So number 49 right here for the play. The question is why, what's the derivative of y equals tan x negative first x squared? So I look back in my notes to find the derivative for tangent negative 1x, which is going to come out to 1 over 1 plus x squared. And then I moved the exponent over to the side, and it was pretty simple. So I just simplified it. And yeah, right here, 4 over 1 plus x squared.
Nice, that looks good. Honestly, I forgot about the notes we did for that to give us the, like, we already know the derivative for inverse trigonometric functions.
Yeah.
Yeah.
That was in our flashcards, right?
Yeah, and for our strategy sheet, that was actually helpful for me.
Yeah, nice. Looks good.
Nice. Okay, for 3.5, I did 7 as well. Share that. Okay, so for 7, it was just the implicit differentiation. And so the initial problem was x squared plus xy minus y squared equals 4. And when you take the derivative, it just goes to 2x, and then plus xy prime minus 2y y prime equals 0. And then I separated the variables so that we had y primes both on one side. And then I pulled them out, and so it was like y prime multiplied by 2y minus x. And then I divided 2x plus y by that, and that got y prime by itself.
I also did that one. I'll pull up my work when you're done. Are you all good with that?
Yeah, I'm good.
Awesome. See here, I just pull up mine for 3.5. I also did it number 7. Let's see. Awesome. Can you guys see my word?
Yeah.
Awesome. So I did number 7. I have my work right here. So question is x squared plus xy minus y squared is equal to 4. This one I chose is pretty simple. Not too much going on. I mean, it's just the product rule with implicit differentiation. So take the derivative of x is you're going to take the entire thing with derivative with respect just to x, and then you're going to use that. So just x squared is going to be 2x, and then plus, and then for the product rule, it's going to be plus y plus x times dy over dx, and then minus, and then it's just going to be pretty simple again for just the y squared is just going to be the exponent rule. So just times dy over dx, and then minus, minus 2y dy dx, and then equals 0 because the derivative of a constant is always 0. And then I rearranged, I put everything that does not have a dy over dx on the other side of the equation to isolate dy over dx. And then I factor out a dy over dx for my left side of the equation here. And then all I had to do then was just divide both sides by x minus 2y. So for this, I got negative 2x minus y over x minus 2y. That was good for me.
Nice. It looks like we got the same thing.
Alright, good. Yeah, I didn't see any differences with ours. I think we did
No,
pretty
it
much the same
wasn't.
thing. Alright, we'll go
Yeah.
ahead and move on to our applies for 3.5. Go ahead and stop sharing.
And for my apply, I did the Bessel function. Is the Bessel function of order 0, y equals j of x, satisfies the differential equation x y second prime plus y prime plus xy equals 0 for all values of x, and its value at 0, or its value at 0 is j0 equals 1. So first we have to find j prime of 0, then use implicit differential to find j double prime of 0. Right here for part A, we know that y equals j of x, and our equation x y double prime plus y prime plus xy equals 0. So, see if I could make this a little bit. So, xj 0 there. No, it's an x. Haha. So this all translates now to x j of x double prime plus j prime of x plus xj of x. Just putting in my j's for all the y's there. And then now we have to find it when x equals 0. I plugged in my zeros, and you'd get 0 times the double prime plus j prime of 0 plus 0 times j of 0. So j prime of 0 is just going to equal 0. And then now we have to use implicit differentiation to find the second derivative of j. Here I have the same equation right here where I just plugged in j of x's into where y's are. And I put these little marks showing that to find the next prime of them. So you're going to get x third derivative j of x plus the second derivative j of x plus the second derivative j of x plus x times second derivative j of x. Got them all right here, and then find all the ones that need to combine on this line right here. And we also know that j of 0 equals 1. So like for this over here, this j is 0. That's just going to be 1. Have our 2 second primes of j. Keep that how it looks. Minus 1 to the other side and divide by 2 to get j double prime to it by itself. The second derivative j to the 0, negative 1/2. And there's a lot of words I had to spit out right there, but there's
Yeah,
no
I
easy way of describing these.
It looks good. I actually didn't even do one of the applies 3.5. Both of them are just like right over my head. I'm actually glad that you showed this one. I was confused. I honestly didn't even think about just plugging in the j of 0 in for the y's and just like exactly what it is. Honestly, it seems kind of simple now that it's put like that. I
yeah,
have to go back and do that one.
I did the same one for the apply, but I got stuck on the second double prime, the J double prime. I got the
Yeah.
first one, like that was pretty simple, just plugging in the 0. But then, what exactly did you plug in for the double prime? Because that's one I just didn't really get.
So when we were trying to do this second one, we already know that the original equation is x, j of x is second prime plus j prime of x plus x,
Yeah.
that thing, right? And if since we know that, we just have to put a second prime on everything, or basically do another derivative for it all to
Right.
find our second derivative altogether.
So my question is like, how come it wouldn't be 0 again? Since
It's not going to be 0 because when you do the primes right here, because this is going to be a product rule. This is also a product rule over here, so it spits out 2 different. I hate how it shows the corners like that. It shoots out 2 different primes.
okay.
And these 2 right here are gonna combine together because they're both just the second derivative of j of x, which is where I get the 2j double prime of x. So I'm gonna have to get rid of that 2 later on, which probably becomes
Okay.
negative 1/2.
All right, I see.
Yeah, that looks good. Yeah, thank you for sharing that. I have to go back and do that one after this, man.
All right, I'll share mine. It's the same, just it looks worse. Okay. So like I said, I did the same apply, and got the first part A as 0, just because you're plugging in the prime for everything else, the derivative for everything else, so it just ends up becoming 0. And then, like he said now, what I didn't do was take the product rule of for part B of the function, which is where you get the 2, which is where it doesn't become 0, which is what I got because I didn't really understand. But yeah, that explanation helped me.
Yeah, definitely. Honestly, I didn't even do the first part of that. I didn't even know what to do. That makes sense. The y is just gonna be the j of x. Didn't even plug it in. Right over my head, man.
All right, I'm gonna share my apply for 3.7.
We're on 3.5.
We are. Oh.
Yep.
I will share my apply for 3.5, which
Oh,
ends
okay.
up being the same one.
You also did that one.
Puzzle function.
Yeah.
I don't blame you. The other one was confusing as hell.
Yeah.
I was like,
Yeah, I attempted
Never
both
mind.
of them and I just got stuck.
okay, 3.5 for apply. So yeah, for part A, just comes out to 0 because they're all 0. And then for part B, you go through, you take the derivative, ends up being like a little bigger and stuff. Then you end up getting the 1 plus 2 t to the second, t double prime 0, and then just flip it to the other side, and it comes to t double prime of 0 equals -1/2. That's what I got, at least.
And for the second part of that, for on part B, you're just gonna take the next higher derivative, even though it says the second derivative.
Yeah, you
Yeah.
just take the derivative there.
Yeah, that's what it is.
Awesome. Okay, yeah, that was yeah.
Yeah. I'm not sure if I did it the same exact way as Jed did.
You got the
What's the
same
bad thing?
answers, so I mean, some of it was same.
Yeah. Either way, it works out for the answer.
Awesome. For my play, I mean, my apply on 3.5. Like I said, I don't have it. I mean, I wrote everything down, so my attempted work is just it's not even like here. I can't even share it if I could. So what I did was I just got like stuck on the first part of the one that you guys did, the bezel function. I couldn't even think of like just plugging in the j of x for the y's. I just didn't even know what to do there. But I attempted the big one, the van der Waal for gas, I believe it was, right?
Yeah.
Yeah, I tried just taking it because it said that like a lot of the variables in there it just says were constants, so I figured I could just plug in like zeros for that, and then it just felt like I was doing it wrong like every step of the way, and I got stuck like halfway through because I couldn't figure out quite how to get rid of it. There were just so many variables in there, just didn't make any
Yeah.
sense.
Right.
I mean, I knew what to do with like an x and a y, but then it started adding in like a's and b's and n's, and I was just sitting here, I don't know what's going on.
Yeah, I didn't even attempt it because I just looked at the thing and I was like, holy crap.
I think maybe I'll go
Like
back,
7
look
variables
at it
in
with
it.
fresh eyes later, but all right now. Awesome. So on
And
to 3.6 now.
Yep.
so for my 3.6, I had to find the derivative of sine of x ln of 5x. I didn't show as much detail as I did for the other one. So it's going to be the product rule again. So I took the derivative of sine of x, which is cosine of x, multiplied by the second one, ln of 5x, plus the first one, sine of x, multiplied by the derivative ln of 5x, which is just going to be 1 over x. And the reason why it's just 1 over x and not 1 over 5x is because that's also a miniature product rule. Like the 5 just doesn't, it just disappears. I even checked online because I was tripping up. I couldn't find anything in my notes about it. And then since we don't have to clean up anything, the answer pops out. It's cosine of x ln of 5x plus sine of x over x.
And that's just the product rule, right? The sine
Yeah.
of x times the natural log of the next one.
It's the product rule. Yeah.
Yeah, all right. That makes sense. I think that's good.
Whoops. All right. For 3.6, I did number 5. Let me share my screen really quick. All right. My computer's lagging out. Okay. So number 5 right here, the problem was what's the derivative of ln 1 over x? So I just rewrote that, f prime of x, and simplified this, took the x out of the denominator, and gave it the negative exponent there. And then from there, just I know already the derivative of ln from the previous, ln x from the previous notes that I had. So I put that as 1 over x and then multiplied that by, that term that's right there. Let's see. And then took the derivative separately of the two terms. This one's going to come out to negative x to the negative 2, and then that one stays there. and then I just resimplified it by moving that back to the denominator and changing the exponent. And I thought that was the simplest form, so I just left it like that.
Yeah, that looks good. I mean, she even said that if you don't see how to simplify it, then I mean, like, don't. It's better just to have like the right answer than just trying to simplify it and get it wrong.
Yeah, it looked pretty simplified to me, so I was
Yeah,
like,
it doesn't look confusing.
Okay, I also did 3, but I did do it, or I didn't do it right.
I think Andre just showed number 5, right?
yeah, I did number 5.
Jed showed number 3, right?
No, I showed number 9. They're
Oh.
pretty similar though.
I
Okay,
did number
That's
3.
where I got confused.
Oh, okay.
But yeah, so I did number 3, which was sine of ln of x. So actually, I might have done it right then. So I don't know. So sine of ln of x. I took that, and then the derivative of sine is just cosine, and then you take the ln of x and put it like on the outside and like multiply it because it was like still part of the function, the sine function, and so then it's just 1 over x. So then it's cosine of ln of x over x.
You just did
And
That looks
the
good.
chain rule. So you did the ln of x first, right on the outside.
Yeah.
yeah,
Sine. Okay.
I just got confused for a sec because I thought I might have needed to do the product rule.
No,
But
I
looks
get it.
like it's all good.
Yeah, since it's in that quantity of sine, you did
Yeah.
do the chain rule.
Okay. That makes
Looks
sense.
good.
All right. Perfect.
Alright, let me show mine. I also did number 3 for my 3.6 OA, so let me just share that. Awesome. So for my number 3, it's pretty simple. I actually did not go forward to simplify it like you did, Eli.
Mhm.
I didn't know if it would just be like the cosine natural log of x over x. That's what I thought. Actually, I put it here in my reflection. I didn't know if I should do that or put it to just like leave it alone or to simplify it. But for this one, it's I thought it was pretty simple. It's just the chain rule because it's the f of x equals the sine of the natural log of x. So it's two things are happening to x at once, so it tells me to use the chain rule. So you take the derivative of the outside of the parentheses, multiply it by just the inside of the parentheses alone, and then multiply it by the derivative of the inside of the parentheses. And the derivative of sine is cosine, and then the derivative of the natural log of x, I have in our notes, it's just 1 over x. Pretty simple. That's all I did. I didn't simplify it as far as you did. But there it is.
Nice. I don't think she matters or she cares either way
Yeah. I mean,
whether or not
I
you
put it in
simplify.
my reflection like my thought on the problem. I don't really know whether or not if I should have combined it.
Right.
I guess we'll see.
Yeah.
All right. On to the applies.
For the apply on 3.6, I did 54, finding the 9th derivative of just x to the 8th ln of x. As you can see, it was really frustrating. So, starting it off, just doing the first derivative, it's the product rule. So it's derivative of the first one times by the second one, and vice versa. That's where we got x to the 8th times by 1 over x, because that's the derivative of ln of x, plus ln of x times by 8x to the 7th. And when you do that, or these are always going to go down 1 power because it's just going to be x over 8 over x. I combined like terms onto the second one, and I just kept doing it, kept doing it, kept doing it. It's the same exact step for all of them, except for I think it's the 8th one here. Do this. It's just when you do x times by 40,320 times by 1 over x, it's just going to be the 40,000 because x's cancel out. Find my like terms and do the 9th derivative is the easiest part because that just goes away. Be 40,320 times by 1 over x.
That looks good. Did you just take like did you just start with the first derivative and just work your way through all the way to the ninth,
Yup, and every single time just combining my
like terms?
like terms and then bringing out the x.
Nice. I wonder if there's a pattern or something you could follow. Like, I don't know, maybe it's something that makes the way higher derivatives easier. Maybe we'll learn something more later in the 3-point section, or maybe even in 4.
I have a feeling it's gonna be something with a big old giant S.
Yeah,
Probably they might use something like that.
yeah, I'm sure it's out there.
There has to be. There's no way everybody just has to sit down if you have to like take the 10th derivative of something. It has to be a little bit easier somewhere.
Right.
hmm All right, so I did the same number 54 for 3.6, except I totally butchered it because I didn't understand that meant taking the 9th derivative. I didn't, like, I just totally blanked on what the 9 meant there on the ddx. So I only took it one time and then simplified it, but I'm pretty sure I just did that wrong. All I did was for the first one, take the regular derivative of the first term, which I got 8x to the 7th times 1 over x, which actually,
It looks like
Yeah.
you should have used the product rule.
yeah, I just did it wrong all around. So Jed's
No, that's alright.
explanation, like when he said it was the 9th derivative, I was like, oh, shoot. So
Yeah.
yeah, that was kind of a loss for me. But
Hopefully Jed's explanation gave you a little bit of clarification on it. Yeah.
yeah, and I don't know if you guys noticed a pattern, but like I just didn't use the product rule when I should have for a couple of these, so I know that for next time.
Yeah. When you go
Yeah.
back to it.
Okay. I also did 54, and I did it the same way. I mean, that we've done it so far. I just sat there and took the derivative all the way down, and then the only time it changed was when we were taking the last derivative because there were no more x's on like the left side, so the left side just went away. Or sorry, it's on the right side for mine. And then since it's just an ln of x and there's no x before it, it just goes to 1 over x. But for the rest of the problem, it's just sitting there and taking the derivative. Still a lot of number crunching, not too difficult though.
Yeah, it looks like you did the same thing as Jed, just kept going with the derivative until you hit the 9th one, and then did you
Yep.
guys get the same answer?
Yeah, we did.
4320.
Yep. But yeah, it was not a fun one.
Yeah, it looks. Let's see. For mine on 3.6, I did 55 actually, and I got stuck. So hopefully you guys can shed some light. Oh, share. All right. So this is 55 3.6 on the apply section. So it says to use the definition of a derivative, so that's going to tell me to take the limit as h approaches 0, and then it gives you a complex fraction, which I know you can just multiply this the entire like fraction by the reciprocal of the bottom, because that's the way fractions work. At least I think that they are. So assuming that was right, I got down to like here, and then I just couldn't figure out how to get them together so I can factor out. Because I know when you're adding or subtracting fractions, you need a common denominator, and I just did not know how to get that here. So I got stuck right here, and this is like as far as I went.
My best guess would be you would have to use the quotient rule of the ln of 1 plus x over x.
Yeah, that's like I mean I'm pretty sure I could have figured it out using like the 3.0 derivative rules, but it says to use the definition of derivative to prove this.
I don't even
So I mean, maybe I took that like wrong, but I took that as in using the definition of a derivative from chapter 2.
Yeah, that was what honestly I thought when I saw the question, and it looks like you plugged it in correctly here.
Yeah,
For the first part.
I got stuck simplifying on the bottom here. I mean, I don't know what more to do. I obviously there's something. I mean, I could just be missing it, but
Yeah.
this is as far as I got. I'll have to look back at it or something. I don't know.
Yeah, I haven't worked on that one yet. As soon as I do, I'll let you know what goes on.
Yeah, I mean, you guys agree that you would use the definition of a derivative rule back from chapter 2 to do this, right? Like that's like what it's asking. Because I mean, if it wasn't asking that, then I just did it the hard way for no reason.
Yeah, I'm pretty sure that's what it means.
All right. But yeah, I mean, this is just as far as I got, which it wasn't too far. I honestly thought I was on to something as soon as I did this and got no longer a complex fraction and then wrote it all out. And I was like, well, I don't know.
Yeah. Yeah, I think quotient rule is probably your best bet there, because
Yeah,
it
it's
would
just, I mean,
take out some of the terms.
are you allowed to use like, oh wait, are you mean multiplying by the conjugate? Or are you
Yeah,
like the actual quotient rule from 3.0?
I was thinking more of the quotient rule, see if that would get rid of some of the terms.
See, that's the thing, because it says to use the definition of derivative. So I don't, like, can you just use the rules while doing it? Like, it's like halfway through it?
well, I think since you already plugged it into the derivative definition thing, I think that counts as using that.
Yeah.
And then you, like, from there, you then solve it. I don't know.
I just don't know. I mean, I didn't think you're allowed to use any of our rules while also using the definition of a derivative to do it.
Hmm.
I mean, I can
Yeah.
try the conjugate, but even then, like I still have two fractions. So I was trying to figure out how to combine them. I didn't look at it really from any other angle.
Right, yeah.
I mean, that is what you have to do for the definition of derivative is the whole as h approaches 0.
Yeah.
I don't know.
Yeah.
I'll work on it as soon as I get a chance, and I'll let you know.
Yeah, that'd be nice. I mean, I didn't really even get that like far. I mean, I'm sure once you can figure out how to get the fractions, if this is even even if this is right here, I mean, if you can figure out how to get the fractions together, I'm sure it's simple from there.
Yeah.
But
And
this is as far as I got.
I don't think graphing this one would necessarily help, because
No.
Yeah,
you don't really know what you're looking for.
no,
Yeah.
I
That
mean,
one just confused me in general, so I just tried to stay away from it.
yeah, it was weird because I mean, it already gives you like the answer, like the limit as x approaches 0 up here. I mean, it's just asking you to prove it.
Yeah.
So I took that as in just trying to do it with the definition of a derivative, but I mean, it could just be more simple than that, and I was overthinking it. I don't know. But
Right.
that's as far as I got. So 3.7.
Yep.
So on to
Yeah.
3.7. I did number 10. particle moves with this position function. That
I think we all did number 10, right?
Yeah.
I did, yeah.
All right, this is gonna be interesting.
could also share insights and then make a question on it. So A, what time does a particle have a velocity of 20 meters per second? And B, what time is acceleration is 0? And what is the significance of this value of t? So for part A, I know that v is just s prime. So here I just put v of t equals s prime of t. So this is our original function. I took the derivative of it. It's just going to be 4t cubed plus, minus t2 squared minus 40t and then plus 20. Then what do I do? Since we have to make it, or since we have to figure out what the value is at, what time does the particle have v of 20? I plugged in 20 for v of t, then solved the equation. I got 3 different things because how it ended up turning out. Got 0, -2, and then 5. And since t is greater than or equal to 0, you could just sub out -2. 2 different things, so t equals 0 and 5 seconds. On to when acceleration is equal to significance of the time. Acceleration is just the next derivative down, time of t. So we have v of t right here. A of t is derivatives to become 12t squared minus 24t minus 40, and then constants are 0. So once again, I just plugged in 0 to solve the equation, and I did the quadratic formula. Got 2 different answers, 3.08 and negative 1.08. Since t is greater than or equal to 0, you can sub out the negative. Significance of the 3.08 seconds is that on the graph of it, when you're looking at the acceleration, these two are both happening at what's it called? At an acceleration is 0, so that means the velocity is at a minimum at this point. Like the graph is at the very bottom.
Alright.
Sense.
That looks good. That's the same way that I did it.
Yeah, me too. I'll just share my thing really quick.
Yeah, it's kind of.
I got the same answers. Dang, dude, I need a new computer. All right. So yeah, same thing for part A. Just took the derivative of the function, set the 20 as v of t equal to the derivative function, and then actually they canceled out if you take 20 away from both sides, which makes it a quadratic thing if you divide everything by t. So then I just plugged it into the quadratic formula and solved it out and got 5 seconds. And then for part B, took the derivative once again and then set 0 equal to that. And once again, it's a quadratic equation. So I was like, oh, I can use the quadratic formula on that. And I got 3.08 seconds. And for this one, I only took, well, actually for both of them, I only took one answer. I wasn't sure that she wanted like any a negative answer or like, you know, it seemed like these were the best ones. So I only took the one, but it looked like you had a couple Jeds, so maybe she wants that.
For A, the reason why I also had 0 is once you get once the 20s cancel out, I saw that I could pull out a 4t because it
Mhm.
is 4t cubed.
Yep.
Yeah.
When I pull out a 4t, that's why one of my answers was 0 there.
Yeah. And I guess that makes sense because 0 is not a negative. So like it does apply to the
Yeah,
time.
that looks good. the same
And
same
then-
answers too.
Yeah, whatever the last part was is just I explained the acceleration as the change in the velocity per second. And the zero just is like when it stops accelerating, like positively or negatively. So
I actually messed up a little bit on this one because let me share my screen. So when I was taking the derivative, I accidentally kept the 20t squared, and then when I took the derivative, I just left it as 20t instead of making it 40t. But besides that, I mean, I did the same thing where I pulled out the t and got the t equals 0. But then I used quadratic formula because I didn't have the right numbers, so it didn't come out nicely. And then I used this same 20 again, which also messed it up, so I had to use the quadratic formula. But besides that, I had the same process.
yeah,
Yeah, that was good.
Yeah.
nice.
Awesome. All right, I'll go ahead and show up mine real quick. Did the same one, number 10 there. Awesome. So for I mean, I declared my variables as his position in meters, t is time in seconds, and then when I went ahead, so I know that it's asking me for velocity and acceleration, which tells me to take the first and second derivative, because the first derivative is velocity, second derivative is going to be the acceleration equation. So part A, at what time does the particle have a velocity of 20 meters a second? See, I didn't really even like do much math here. I just simply asked myself, what would make this equation be 0? Like the actual part of it. I set it equal to 20. In retrospect, I shouldn't have. I mean, if you just ask yourself that, it looks like if you just zeroed out everything, it's adding 20 on the end. So you just put a 0 in there, cancel everything but a positive 20. So it just be that this is just true. So I wrote out, so at 0 seconds, velocity is going to be 20 meters a second. And I didn't really do like any of the equations. I didn't really see the need to. I mean, if she wants us to do that, I might just go back and write it down. But I mean, I just saw the positive 20 there and just thought like, there it is. And then
Yeah.
for part B, using the acceleration equation as double prime or the second derivative, time. So at what time is acceleration 0, and what is the significance of this value at t? Oh, I actually, I don't think I answered this second part of that. I'll have to go back and write that down. So it's simple. You're just gonna zero out this equation because it's asking the time at 0. So 0 is equal to this equation, and then I saw that you can just plug this into the formula. What is the formula called? The
Quadratic.
yeah, that one. Plugged it into the quadratic formula, and then just put it into my calculator. And I did adding first and got 3.08. I didn't even write down the minus one, the negative. I think it's like negative 1 point something. And I just knew that it was 3.08. Honestly, I was under the impression that acceleration couldn't be negative. Is that true? Because
I think it can be negative.
With the terms of this question, though, it says t has to be greater than or equal. Just like
0. Yeah. So
Oh, I guess that's
so
true.
like in this context, like no, like there's no way that acceleration can possibly be 0. I mean not 0, negative.
Yeah, I thought you just meant in general.
No, like sorry, I guess I should have explained it a little bit better. So yeah,
Yeah.
because I plugged this in, got that, and then I plugged it 24, minus the whole thing, and I got a negative number, so I just kind of knew that just wasn't gonna be it. So
Right.
so good there. I'll have to go back and answer the second part of B. What is the significance? I didn't write that down.
I did answer that and forgot to say it. But basically, I just said that the significance of it is that it's when like the function is like moving at a constant speed because since the only time when the acceleration is 0, it's the only time it's not accelerating or decelerating. But I don't know if that's what you wanted or not.
I mean that sounds right. I mean, it's kind of hard, you know, because it's so vague. Like, what is this? What is the significance? I mean, it really could be a lot of things.
Yeah. Except, like we said, in this one at least, it couldn't be decelerating, right? Because it
Yeah,
has to be
'cause
greater than or equal to 0.
yeah,
Okay. Yeah, I totally forgot about that actually.
yeah. I just
The
guess
B.
that's how I took it. Jed, your explanation was that you knew that it was gonna have to be a minimum, right?
Yeah, so like since the acceleration popped out a positive and negative answer at the same time, means that the velocity function is at a minimum.
Okay.
All right.
Yeah, that makes sense. Yeah, because the little chart thing, like when you know the chart, it was in our notes. It had acceleration, velocity, and then when those are positive and negative, and what that means, speeding up, decreasing, or staying still, right? So all right, now we're gonna do our team crafted questions. Which questions were we thinking about again? We can do 3 point the number 10 for our apply team crafted.
Yeah. Is
Yeah.
the 3.7 number 10, and then I don't remember the other one.
And we can just make it here.
Talk about why we would need to find implicit differentiation.
Awesome, yeah, that makes sense now. So did you want to do number 7? I think we all did different ones except for I think me and Eli both did number 7, right?
Yeah, and then I did number 13 for that part.
Yeah, I did 7 and 49, but I talked about 7.
So you guys want to talk about 7 and then we can just talk about implicit differentiation as like a whole. Does that sound good to you guys?
Sure.
All right, I'll write that down. So, I mean, this is just like a whole like team crafted question. I'll go ahead and go over 3.5 number 7 for our play real quick. This is just the implicit differentiation x squared plus xy minus y squared equals 4. And then you just, I mean, we already talked about this, just, you know, take it. So, a good question here I can think of might be, it's nice to know, like, it's going to be very helpful to know how to find the derivative of equations that are in implicit form, because you're not always going to be able to get it into a better looking form to make it easier for yourself. So just being able to right off the bat do that's nice. So I think that's going to be very helpful, especially in the future. And I think maybe like a question on this could be, what other implications can this have? And I mean by that, not necessarily of like other equations, but like when in life are you gonna see, you know, everything in the perfect form, right? I mean, it's not always gonna be set up nice and neat. You're gonna need to know, like, when it looks weird and all messed up, that you're gonna need to know how to do it anyway, you know.
Mhm.
So, and like, what other applications is this gonna have in the future?
Yeah, you could look at variables in life as like different, well, I guess variables, but like just different things that are gonna apply to the situation.
Yeah, I
So,
mean, I'm assuming that we're all STEM majors in
Yeah.
your considering we're taking a calculus class.
yeah.
So we already know this is gonna help out later. I mean, this is just the foundation.
Yeah.
I wonder if future there's going to be more variables that you're going to have to do differentiation with, not just x and y.
Yeah.
That's good. Only one of us submits the questions, right?
Yeah.
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 All right.
I'd have to like speed the work right after this. I can't do that.
Okay.
Yeah. All right. I'll do it. I mean, I'm already turning in the video.
Okay.
Okay. Just
So-
let me know if you have trouble at least with the questions, and I should be able to do it later today if you just want to focus on the video. But if not, if it's easier for you to just do both, that's cool.
I have like a breakfast here soon, so I might be able to do it like right after. So Andre, if you just want to take care of it, actually that'd be awesome.
Okay.
Do
Let me
you
write
plan any more
down.
questions?
Do we have to write a question for the apply too, or just the play?
Both play and apply.
Yeah.
Okay.
Honestly,
So,
if you want to write down just both of our questions, I like Jed's honestly more. Like other variables, like will there be more to it than just x and y?
okay.
I can send you a picture or share my doc with you of my work for
And what
3.5 for the question 7.
So all I have to do, right, is submit like just our question. Is there going to be more to like situations in life, like more variables than just two x and y?
Yeah, like you know, I don't know, maybe in the future we're gonna see a z in there somewhere.
Yeah. Okay.
But I guess I guess we might, right? Z's
Yeah, x, y,
Well,
z is always going.
yeah z's fuck it's I always say depth, but I know that's only kind of right. It's like position like in space because it's three dimensions.
Right.
So who knows? Maybe we'll be able to use this for z too.
I'll probably be going to fucking Coke 2. Ugh.
Yeah.
For 3.7,
Hey, do you want me to stop sharing and you can share? Or do you want to just look at mine?
we can just pull up yours since you already
Alright.
have.
Yeah, it's just right here.
I think a good question to come from that is why would we need to find velocity and acceleration and possibly even the jerk of the equation? Jerk, if you
Right.
guys don't know, is the third derivative.
Yeah. I mean, I can see maybe that's useful in like certain fields. I mean, it might be useful in mine. I'm going in for aerospace engineering, so who knows? I mean, it seems important, right? But I mean, I can see that. You know, why do we actually need to know the velocity? Is that's something that has already happened, but I maybe knowing it like for what it's going to do.
Yeah. Seems like, yeah, like at first, or yeah, without thinking about it very much, finding the jerk like can seem kind of useless. But then when you think about it, like it is telling you how the acceleration changes over time, which does seem useful with a lot of like real life examples.
Yeah.
yeah, I think this question is like set up just basically like so many. Like I don't know if you guys took physics in
Yeah.
college or in high school, but like so many of those questions were literally real life situations that they like pulled from whatever.
Yeah.
Yeah. I did notice that a lot of these looks like physics questions.
I found this old photo from my physics class, and we talked about going further and further through things, and they're all lining up to derivatives. So it goes the velocity, acceleration, jerk, and then snap, crackle, pop, block, drop, shots, and pats. So it's all the way down to the 10th derivative.
Jeez.
Dang.
I wonder why we would need to have so many.
Yeah.
Right.
It's like obviously there's a reason if we have words for them.
Well,
Right.
yeah, obviously.
Yeah.
Maybe
So-
another question? Are we just gonna stick with that one, or do we want some more questions going on here?
On another question.
All right. You said yes, right? Yeah, yes to another question.
Yeah, that's fine.
Alright.
So what? Wait, hold on. So what was the like first one overall?
What is the like importance of finding like the velocity of and velocity, acceleration, and jerk of
Okay.
these things? Not necessarily
Alright.
just of like a particle, but like really anything. I mean,
Derivative.
Yeah.
honestly, I think that's pretty good. I know, Jed, you got a bolt, right?
Yeah, I was supposed to be at work at 10, but I woke up late.
Oh shit.
I let them know, so like they're not gonna get too mad at me.
I mean, as long as you're all good, I think we're pretty wrapped up here. We did our intro, did everything else, did the
Yep.
crafted questions, and then we're all
Sure
good.
to
So
work.
I'll submit this when I can. Probably here soon if it gets done in time. I'll go ahead. Are we all good, or do we need to keep
Yeah,
recording?
I think we're good.
Yep, I got the questions down.
All right, I'll go ahead and stop the recording.